Hey everyone, we're really getting to the heart of the material when it comes to group theory. And so remember last time what we did, we defined the quotient group, right? So what we have, and I'll just kind of summarize, when H is a normal, and this is really if and only if, but the important part is in this direction. So when H is a normal subgroup of G, we have the group G mod H under the operation of coset multiplication. And what you do to multiply, I didn't need these parentheses, I just made things more complicated. When you multiply the left cosets, the way to get the answer is you multiply the coset representatives A times B. We showed that is well defined if and only if H is a normal subgroup. And so, I mean, it's taken a while. We've been building and building and building, and now we're really to the fun part of this class. I mean, it's all fun, but now it's really getting exciting, at least for me, and hopefully it's getting exciting for you. And so what we have is this new way to construct groups, starting from an existing group G by taking this set of left cosets where H is a normal subgroup. We create this new group. And so one of the things that we want to understand is, to what extent do the properties of G carry over into G mod H? So that'll be one of the things that we want to consider. Let's look at a couple of examples first, and then we will definitely need some tools, some techniques to understand how G mod H behaves, right? So I mean, understanding a quotient group can be a difficult process, right? I mean, they can be kind of complicated, in fact, extremely complicated. And so we will need some techniques, some tools, some machinery, I guess you could say, to deal with this. All right, but let's look at a couple of easy examples. So let's let n be a natural number, and let's look at, and consider Z mod NZ, right? So the set of left cosets, the quotient group Z mod NZ. Now you might say, well, did you jump a little bit quick here? You called it a quotient group, but remember, you need to have the denominator, if you like, to be a normal subgroup of the numerator. And so I should just say, note that since Z is abelian, NZ is a normal subgroup of Z, and so Z mod NZ is a group. So that's the one nice place where you don't even need to apply the normal subgroup theorem. If you're working in an abelian group, when the numerator is abelian, every subgroup is normal, and so the quotient, right, the set of left cosets is automatically a group. So let's just take a look at this. So let's say, note that the set of left cosets, so Z mod NZ, consists of the cosets. So I'm just going to start writing them down. Of course, there is NZ. Then there is 1 plus NZ. Remember, NZ, that's the multiples of N. 1 plus NZ, that is things of the form 1 plus N times A, I guess. Take all multiples of N and add 1 to them. Another way to think of it is the set of all elements, so that when you run the division algorithm, you get a remainder of 1. Then there'll be 2 plus NZ, dot, 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 all the way down to, now notice what will happen when we get to N minus 1 plus NZ. That's going to be the last one, because N plus NZ is equal to N. Okay, so here's our group. And let's see if we can say anything about it. Yeah. I'd like to get some sort of hand on how this group behaves. So I should say, I guess I haven't really finished my sentence here. I was going to say, and if I look at m times 1 plus nz, that's equal to m plus nz. Remember, this notation here means add 1 plus nz to itself a bunch of times. And so, if, for example, I wanted to get this coset right here, 1 plus nz plus 1 plus nz gives us 2 plus nz. If I wanted the next one, which would be 3 plus nz, it would be 1 plus nz plus 1 plus nz plus 1 plus nz. And so, in fact, now, by just looking at this right here, by adding 1 plus nz to itself m times, I get the coset 1 plus nz. And so what am I getting at here? It follows that z mod nz has a generator. That element right there, 1 plus nz, is a generator. And so z mod nz is a cyclic group. 1 plus nz is a generator. Now how many, so now we've shown that z mod nz is cyclic. Its order is exactly n. And so that tells us, so as a consequence, z mod nz, well, let's see. Every cyclic group of order n is isomorphic to Zn. Okay, so there's one example of there's our first example of a quotient group. Let's look at another one. So the next example, what I'd like to do is look at R mod Z. Right, so R is an abelian group under the order of addition, under the operation. I said that weird. R is an abelian group under the order of, why do I keep saying order? Under the operation of addition. Because it's abelian and Z is a subgroup, we have that it's a normal subgroup, right? And so this is a group. And so what does a typical coset look like? So a typical element is of the form. So how would that look? It would be some real number plus z. So it would be something like, so it's of the form r plus z. And so what will that look like? Well, what you do is you take every integer and add r to it. So r could be any real number. R could be 1/2. It could be a fraction. It could be the number e. It could be the number pi. So r plus z, it's equal to ... r minus 2, r minus 1. R plus 1, r plus 2, ... going on forever in both directions. All right, so there's what a typical coset, a typical element of this group right here looks like. Now, I guess we should think about what it means for cosets to be the same. So we'll say, we can say, and r plus z is equal to r prime plus z, right? So if we take two real numbers, they're going to give us the same coset if and only if r minus r prime is an element of z, right? There's the typical way to decide whether two cosets are equal. And so what does that mean then? Two cosets are the same if and only if the difference between their coset representatives is an integer. Right? The difference needs to live in z. Now, what I want to do, I'd like to get a feel for what this quotient group looks like. So I'm just going to kind of jump into it. So let's define I guess we'll call it F, from, where do I want to go? I want to go, well, okay, I'm just going to say it. So I'm going to go from R mod Z to U, the unit circle in the complex plane. I want to define it by F of, okay, so a coset here would be an R plus Z. And I want to equate it with, how are we going to do this? E to the 2 pi, E to the 2 pi I times R. All right, so there's a legitimate function. And let's see. Okay, what do I need to do? What I want to do actually in the end is show that this is an isomorphism. So there's a few things I need to do. The first thing, and this is not obvious, I mean, it's not completely clear that this quotient group is somehow connected with the unit circle. So let me finish off. I'm going to prove that this is an isomorphism, and then I want to kind of back up a little bit and see why one would ever suspect that maybe this quotient group here has anything to do with the unit circle. So first, let's go through the details and show that this is an isomorphism, and then we'll kind of slow down and say, okay, where did this isomorphism come from? So here we go. First thing I need to do, so we show that F is an isomorphism. And I'll do some of the details, and I'll leave some of the details for you to check. The first thing I need to do, notice that I've defined a function on a set of equivalence classes. I immediately need to show that it's well defined. All right, so to see that F is well defined, let R and R prime in Z in R be such that R plus Z equals R prime plus Z. Okay, I'm about to erase it, but what does that mean? That means that R minus R prime has to be an integer. So we can say then R is equal to R prime plus K for some little k in Z. Now, F of R plus Z, by definition, that's e to the 2 pi IR. But then R is equal to R prime plus K, so this is equal to e to the 2 pi I times R plus K. We can split this up as e to the 2 pi IR times e to the 2 pi IK. And now, e to the 2 pi I times k, right, that's equal to 1. And so this is equal to e, sorry, I lost my prime. That should be a prime, and that should be a prime. So this is equal to e to the 2 pi I R prime times 1. And that's equal to f of R prime plus c, right? So when we have the same input, we get the same output, right? And so we have a well-defined function. Next, I'll show it's a homomorphism. So now let's let I guess just R plus Z and R prime plus Z be in R mod Z. Then if we look at F of R plus Z plus R prime plus Z, so I'm taking two cosets, doing the operation, which is addition, plugging it inside there, and then this would be equal to F of R plus R prime plus Z. Our formula says this is e to the 2 pi I times R plus R prime, which we can then split up, and now it should be clear that this is a homomorphism. So this is e to the 2 pi I R times e to the 2 pi I R prime. That's F of R plus Z times F of R R prime plus Z. Okay, so therefore, F is a homomorphism. And then I'm just going to leave the details for you, so I'll just say check. Oh, you know what? Actually, no, I'm going to show one-to-one now. And then I'll let you check onto. Okay, and the reason I want to check one-to-one in, live like this, or not live, but I want to actually do the process. Remember, when it comes to homomorphisms, there's a way to check that it's one-to-one that doesn't require you to use the set theory process, right? So to see that F is one-to-one, we show that the kernel of F, remember, to show that a homomorphism is one-to-one, it is enough to show that the kernel is equal to, or the kernel is trivial. So in this case, the kernel of F is trivial means what? All right, so we need to remember what's the identity in Z mod, or R mod Z. The kernel consists of a single element, just the coset Z, the identity coset. Okay, so to do that, let's say suppose F of R plus Z is equal to the identity. Okay, so who's the identity in U? Remember, U is a subgroup of the multiplicative non-zero complex numbers. In other words, the identity is equal to 1. Then, what do we have? E to the 2 pi IR is equal to 1. And so when does that happen? It happens precisely when, so that's, and so R is in Z. Well, if R is in Z, then this coset is equal to the Z coset, the trivial coset. So this implies that R plus Z is equal to Z, right? Whenever you have a coset representative that lives inside that piece right there, it gets sucked inside, and so we're left with this. Therefore, the kernel of F is contained in the set consisting of just the coset Z. The opposite direction is automatically true. Okay, so by, I don't remember the theorem number, but I want to say it. So it was 14 point something. 14.2. No? Oh, was it in 13? I think it was in 13. Hold on. Oh yeah, 13.2. So by corollary, 13.2, we have that F is 1 to 1. Now you might say, what's going on here? You only showed inclusion one direction. The opposite direction always occurs, right? The identity always gets sent to the identity, right? And so the identity is always in the kernel, right? So the reverse inclusion is always true. And let's say check. It's pretty obvious. So check that F is onto. Right, and that completes the proof. I wasn't actually doing a theorem here, we're still in an example, but that completes the goal that we had, which was to show that F is an isomorphism. In other words, right, so our conclusion is that R mod Z is isomorphic to the unit circle. So, all right, there's the details of the proof, but now where did this come from? Why would, I don't know, why would anyone ever even suspect that? So let's back up for a second and think about what R mod Z would look like. All right, so we have the real line and a particular coset. So let's mark some points here. So a particular coset, how does that work? Well, if that's R right there, then the elements in our coset are integer distance away. I know this is a little bit lopsided, right? But this element right here, R minus 1, that's R plus 1, that's R plus 2, R plus 3. All the elements that are an integer distance away from R live inside live inside our coset. All right, so R plus Z consists of, remember all the things of the form, so it'd be like R minus 2, R minus 1, R plus 1, R plus 2, and so on. So, here's the thing to notice. Every coset has a representative that lives inside the interval from 0 to 1. So let's say, notice, every coset R plus Z can be expressed as A plus Z, where A lives between 0 and 1. Everybody has a coset representative right there. So now, what this does, and what you want to picture, is let's take the real line, and let me try to do this a little bit better here. Let's take the real line, chop it up into intervals, and then stack them above each other, right? So I'm going to have an infinite stack of intervals, right? So maybe this one right here is the interval 0 to 1. And then this is the interval 1 to 2, 2 to 3. This would be minus 1 to 0, minus 2 to minus 1, minus 3 to minus 2, and so on. This goes on forever, upwards and downwards. And so now, if we wanted to identify a particular coset, like let's see, what did I do? I marked my R between 0 and 1, right? So if that's R, then there is R plus 1, there is R plus 2, there is R plus 3, R minus 1, R minus 1, r minus 2, and so on. So if you wanted to identify the coset now, this makes it easy. Just draw a vertical line. Whoop, I missed that one right there. And the vertical line hits all the elements in the coset. All right? So what does this quotienting process do? It essentially says in R, consider the unit interval right here. All right, so there's 0 to 1. And the coset A plus Z, where A lives between 0 and 1, corresponds to this element, little a. Right? Every coset corresponds to an element sitting inside the interval from 0 to 1. So there's this correspondent, coset to elements within the unit interval. In a sense, what it does is it takes the real line, chops it up into a bunch of intervals, and then smashes it down into a single interval. And then we have to recognize, oh, wait, the coset 0 plus z corresponds to the coset 1 plus z. And so really, then these two are the same. We should make sure that they look the same. And so that coset right there is the 0 coset. This corresponds to 0 plus z, which is the same as 1 plus z. And so what we have then, now you can see that's where this idea that the shape of this coset is actually a circle, or that this quotient group is actually a circle. That might be a lot to digest. I want you to go through this and sort of assimilate this. When it comes to quotient groups, it helps to feel it inside. And I know that sounds weird, but it does. You want to feel what R mod Z looks like, right? Now, I'm going to leave off with one of the most important techniques in algebra, right? And we're going to look at the group theory version, and we'll see the ring theory version of it next quarter. So this is called theorem. So the number is 14.4, and it's called the first isomorphism theorem. If you want to identify the most important theorem in algebra, this has got to be it. So it goes like this. So let's let I guess let's call it phi from G to H be a homomorphism. Then G mod, the kernel of phi, is isomorphic to the image of phi. This theorem connects the idea of homomorphism and the idea of quotient. And what this does is an extremely powerful tool for understanding quotient groups, right? It allows us to get an isomorphism between a particular quotient group and a subgroup of the codomain, right? The image of phi lives inside H, right? It's a subgroup of H. Okay, so we need to prove this theorem. This is the most famous, I don't know how to say this. This is as important as it gets. All right, it's so important that I need to get myself another Pepsi before I do the proof. Oh. There's not a lot of good things that come from filming in the office, right? I mean, it's kind of cramped. I only got one board. I can't spread out. I can't see you, but at least my refrigerator's right there, so if I need another drink, I can access it. All right. So what do I need to do? I want to show that we have an isomorphism here. So that means that I need to come up with the isomorphism. So I'm going to define, and I want to call it, I don't want to call this one, I call it phi bar. Okay, so phi bar from G mod kernel of phi to right to the image of phi by, so I need to tell you the formula for this. And so what are we going to have? Phi bar of a coset. The coset will be something of the form, what symbol do I want to use here? Oh, I guess just little g. Okay, little g times kernel of phi, right? Those are the elements inside the codomain. Inside the domain, right? They're left cosets of this form. And for the output now, I need an element of the image of phi. And so there's really only one thing, sort of the obvious thing to do. The output here is going to be phi of g. Okay, so there's a formula, and now we want to show that this actually gives us an isomorphism. Notice that what I've done, I've defined a function where the domain is a set of equivalence classes. The first thing I need to do is show that this is well defined. So we first show that phi bar is well defined. So to do so, let's choose a couple of cosets. So let's let G and I guess G hat be in G, where it gives us the same left coset. So where G times kernel of phi is equal to G hat times kernel of phi. Okay, so what does that mean? So then G inverse times G hat is an element of kernel of phi, and so G inverse G hat is equal to, let's call it little k, for some little k in the kernel of phi. And then I want to unravel this. So this means that G hat is equal to G times K. Okay, so now what I need to do if I want to show it's well defined, I need to show that the same input gives us the same output. So now let's look at phi bar of G hat times kernel of phi. That's equal to, so let's see, the formula tells us that this is equal to phi of G hat. But G hat is equal to G times K, so this is phi of GK. Now, since phi is a homomorphism, I can write this as phi of G times phi of K. But what's this? This is equal to, well, let me write it like this. So what do I know about K? K lives in the kernel, so this is the identity. So this is phi of G times times the identity in, I guess it'd be the identity in H, which is equal to phi of G, which is equal to phi bar of G times kernel of phi. All right, so that shows that it's well defined. What's next? I need to show that it's a homomorphism. That's going to be just about automatic, but we got to work through the details. So let's let, how about let's call them A and B be in capital G. Then if I look at phi bar of A kernel phi times B kernel phi, you know, I just realized I should have at least said some words, right? When I wrote this down, how do I know that this is a group? I know I'm interrupting my own proof here, but I should have said this right at the beginning. We learned last time that the kernel of phi is always a normal subgroup, right? That was, I think, 14.2, I think was the 14.3. What was it? Oh yeah, 14.2. And so I jumped. I wish I wouldn't have jumped so quickly. This is guaranteed to be a group because kernel of phi is automatically normal. So sorry, I should have said that right at the beginning. Okay, so what is this? This is phi bar of AB times kernel phi. That's the operation within the quotient. The formula, this is equal to phi of AB. But then phi is a homomorphism, and so this is equal to phi of A times phi of B. And then we put things back together. This is phi bar of A kernel phi times phi bar of B kernel phi. And so phi bar is a homomorphism. So it remains to show one-to-one and onto. And this, by the way, this is clearly onto by construction. So let's do the onto part real quick. If X is in the image of phi, then X is equal to phi of A for some little a in G. So now, phi bar of the coset A times kernel of phi is equal to phi of A, which is equal to X. And so, right, I chose somebody in the image, somebody in our codomain of phi bar, right? So I chose somebody in the codomain of phi bar. I produced somebody in the domain of phi bar that gives us that as the output. So we'd say, and so phi bar is onto. Last step, I need to show that phi bar is also one-to-one. So suppose that, let me say it like this. So now let's let I don't know. Let's use a different symbol. How about Z? So let's let Z in G be such that phi bar of Z kernel phi is equal to the identity. In other words, I'm choosing somebody in the kernel of phi bar. Right? This element right here, the output under phi bar is equal to the identity. So this coset right here is in the kernel. To show that it's one-to-one, I want to show that the kernel is trivial, so I need to show that this is the identity. Right? Z kernel phi is the identity in G mod kernel of phi. Okay, so then we have, okay, so the formula tells us that phi of z is equal to E sub h, and so z is an element of the kernel of phi. It follows that the coset z kernel of phi is equal to the coset, the identity coset kernel of phi. And so, it's going to look a little bit funny here. So the kernel of phi bar is equal to the set consisting of a single element, and that single element is the kernel of phi. In other words, the kernel of phi bar is trivial. It consists of just the identity coset. By, what was it, 13.2 or 13.3? I can't remember. 13.2, I think. Yeah, 13.2. So by 13.2, phi bar is 1-to-1. We need a concluding sentence. Therefore, phi bar from G mod kernel of phi to the image of phi is an isomorphism. Now, this proof, this theorem is a big deal. The proof is not quite one that brings tears to your eyes. It's not quite that deep, but still, this is an important theorem, and the technique within here, the techniques that you see within this proof are important also. So you need to learn this proof, right? You need to understand this proof and see why it works and how it works, right? Because what we're going to do is we're going to make use of this theorem in many cases, right, to conclude that a certain quotient group is isomorphic to some other familiar group. Right, we will use this theorem. Okay, so that's a good place to leave off. We'll do examples next time. All right, so we'll see you then.